So now, students, let's continue with the harmonic oscillator. We have already done. We have subjected this harmonic oscillator to quantum mechanical equation, what's generally known as Schrodinger's wave equation. What we obtained is that the energy of this harmonic oscillator is quantized, and the spacing between different energy levels is same, and that's equal to h nu. And we found one important additional thing, that for n is equal to 0, we have energy of the oscillator, and that's h nu times 0 plus 1 by 2. So this energy that we have is called as 0 point energy. And now we would like to write down the normalized wave function for this harmonic oscillator, and then we would like to see the behavior of wave function, and that should be the motivation of this video. And if we rightly remember, we have the wave function, the general wave function that we have for harmonic oscillator, that is psi n is a e to the power of minus y squared by 2 h n of y. This is our wave function for this harmonic oscillator, and this a is a constant, and definitely it represents the amplitude, and this hn of y is Hermite polynomial. So this hn of y is Hermite polynomial. Now, and we have the generating function for this Hermite polynomial as that's minus 1 raised power n e to the power of y squared by 2, then dn by dy n e to the power of minus y squared. That's it. And what we do is that we normalize this wave function, and we have certain assumptions. If we rightly remember, y is equal to alpha, it is x root alpha, y is x root alpha. We have taken this assumption in the previous video, where we have come up with the eigenvalue solution of harmonic oscillator, and from there we have a correlation that y is equal to x under root alpha, and we also know that this alpha is chosen there as m omega by h cross. So these are the two important equations, and we understand how to normalize, and when we normalize this wave function, all we do is we find this a. So using normalization, so I will directly write down the value of this a that's evaluated, and that value comes up to be so crazy, under root of alpha by 2 to the power of n factorial under root of pi whole raised power 1 by 2. And we certainly understand that we have a condition for that, that this normalization goes like minus infinity to infinity, psi star psi dx is equal to 1. So using this equation, we are in a position to calculate the constant a that appears in the solution that was proposed for the differential equation, that we obtained by moving on from Schrodinger's wave equation. And so here we can write down this normalized wave function, and this normalized wave function So what would be that? That would be psi n is under root of, should I go with this under root? Okay, let me go. It's under root of alpha divided by 2 to the power of n. Then we have n factorial, and this is under root of pi. And then we will have e to the power of minus alpha x square by 2. Then we will have hn of under root of alpha x. What we have done is we have used this transformation. Instead of y, we have used x under root alpha. Okay, so that's how we have got this term over here, and then this Hermite polynomial it's the function of y. So instead of writing y, we have written it down in terms of alpha and x. That must be the case. Now, what is our intuition here is we have a normalized wave function. We want to understand. We want to get this wave function for first three important states of harmonic oscillator, and for the first case, what's called as ground state. We would like to have ground state wave function, and we understand that for ground state, n is immediately equal to 0, and hn of y that we have for n is equal to 0, right? So from this equation, if we go to the generating function, where is that? If we go to this equation, we will be able to find this hn of y, and this hn of y will be h0 of y. So what I have is minus 1 whole raised power n, that's 0. Then I will have e to the power of I will have y squared, and then I will have the double. Since n is equal to 0, so I have to go with the same e to the power of minus y squared. So that will be the case, and this h of y is going to give me 1. And also in this equation we have n factorial, so 0 factorial is going to give me 1. So from these calculations, we can write down the wave function for the ground state of this harmonic oscillator. So here we have then what I'll call that psi 0. That will come out to be very simple. It's alpha by pi whole raised power 1 by 4. Then e to the power of minus alpha x squared by 2. This is what we will be getting, and what is important here is that that what we have used here is y is equal to x under root of alpha back into the equation. So this is my my wave function for the ground state of this harmonic oscillator, and if we plot this this wave function, what we see is these are, say, classical limits. What we see is that the wave function behaves like this. Okay, so this is my, say x is equal to minus a, and this is my x is equal to plus a, this point. Okay, so in the y-axis, what I have is psi 0. Right. Now, if we go to the first excited state, so what is evident from this plot is that the wave function for quantum mechanical harmonic oscillator is crossing the limits of classical harmonic oscillator. It's crossing it. Okay. So it's showing its existence beyond plus minus a. So we can, in similar fashion, we can calculate this wave function for first excited state. So first excited state wave function. So for that, what we have is n is equal to 1. That's the case, and in hn of y that we have to use n is equal to 1. Okay, so is that. So I have here is my hn of y. So I will have to go with single derivative, and what am I going to get here is it will be minus 1. So what is it, hn of y? This will be equal to minus 1 whole raised power minus 1 whole raised power 1. Then what I'll have is I will have e to the power of y square by 2. Then I will have the differentiation of e to the power of minus y square. Okay, that should be the case. So hn of y will be minus times e to the power of y square by 2, and the derivative of this will be minus 2y times e to the power of minus y square. That should be the case. Yeah. Here we are choosing e to the power. We have e to the power of y squared. Okay, so with this, what we are in a position to get from here is you will have minus will give me a plus, and you are going to have 2y from here. Okay, so for y I have what? Y is x under root alpha. So this 2y will be 2x under root alpha. So I can immediately use it in my wave function psi 1, and from there what I'll have under root of alpha by 2i under root of pi raised power, it will be 1 by 2. Then here I will have e to the power of minus alpha x square by 2 times twice under root of alpha x. So this is going to be the wave function that we will have for the first excited state of this harmonic oscillator, and when we plot this down, this equation, what we obtain is a behavior like this. We have to have the classical limits first. Okay, and what's the behavior like? It's, let me have some reference line here, and so it's going like this. It goes like this, and it goes up like this, and it crosses like this. And see, this is why my psi of 1, and this is my x equal to minus a, and this is my x equal to plus a. So this is giving me the wave function for the first excited state of this harmonic oscillator, and under similar considerations we can have psi 2, psi 3, and in every case you will have n equal to 2 for psi 2, you will have n equal to 3 for psi 3, and so on and so forth. And we will have a range of wave functions that can be plotted, and what we observe, what important point we observe is that the wave function for this harmonic oscillator, it does exist outside the classical limits of a harmonic oscillator, and that's an indicator of the wave function passing this level from both the sides of this classical limit that we have.